Hey guys, it's Margot at Lanterna here. I'm a maths tutor for Lanterna and I'm coming to bring you a number of online IB Maths videos for the applications and interpretation syllabus. So today we're going to be looking at the first part of vectors covering the standard level content. So this includes point 3, point 10 to 3.11 on the syllabus. And in particular, we're going to be looking at vector representation and vector operation. So really building on that basic knowledge of vectors. So let's get started. First of all then, vector representation. We're going to have a look at the key ways in which we denote a vector in 2 dimensions. So the first way to do this is using our matrix representation, where the top component of our matrix here denotes our x component or our horizontal component of our vector, and this bottom component here relates to our vertical component or the y component of our vector. So if we look at the vector u, which I've drawn in this diagram here, we can split it up into its horizontal component, which has a magnitude of u1, and its vertical component, which has a magnitude of u2. Now, another way to represent this is using our unit vector representation. What are the unit vectors? Well, the unit vectors are vectors of magnitude of 1, and I hat is our unit vector in the positive x direction, and j hat is our unit vector in the positive y direction. So to use that in our representation, what we're saying is that our vector u is equal to the magnitude of the horizontal component times this vector I, which has a magnitude of 1, so it's not going to change the magnitude of that horizontal component, but it's informing us that it's in the x direction. And to that, we're adding our horizontal component magnitude u2 times our unit vector j hat, which again has a magnitude of 1 in the y direction. So we can extend this very simply into 3 dimensions as well by simply adding a component in our z direction and introducing also a new unit vector k hat, which is our unit vector with a magnitude of 1 in the positive z direction. So vector operations then. First of all, I want to have a look at negating a vector. So what do I mean by negating a vector? Well, if we have a vector u, we're asking what does the vector negative u look like? Well, negative u, the magnitude stays the same, but the negative sign informs us that our new vector is now in the opposite direction, which means our negative u looks like this. Second of all then, addition and subtraction of 2 vectors. If we have a vector a and another vector b, what will our vector a plus b look like? What we need to do is align the head of one arrow to the tail of our second arrow. So it's going to look something like this if we're adding a and b. A, we want to align the head of that arrow to the tail of our b vector. So then overall, what we're doing is we're moving from the start of vector a to the end of vector b. So our vector a plus b is going to look like this. Third of all then, multiplication by a scalar. If we have a vector u right here, what if we want to multiply that by a scalar such as 3? We want 3u. Well, remember, a vector is a quantity with a magnitude and a direction. And if we multiply that by a scalar, which has only a magnitude, you can imagine that only the magnitude of the vector will change and that its direction will remain unchanged. So if we have 3u, for example, then that is going to just be in the same direction of u, but have a length which is 3 times as long. So overall 3u will look something like this. Finding the magnitude of a vector then. Well, the magnitude of a vector essentially translates to the length of that vector, or the length of that line we've just drawn in space. This is easiest to look at considering our triangle trigonometry that we know. So we're trying to find the length of this vector. Now, if you remember looking at how we represent this vector, we said usually we know its horizontal and its vertical component. Well, in that case, recognizing that this is a right angle triangle, we can see that the magnitude of our vector, which we denote by putting it in straight brackets, we can find just by using Pythagoras' theorem. So if this is our u1, our horizontal component, and our u2, our vertical component, our magnitude is the square root of u1 squared plus the square root, plus u2 squared. Finally then, a unit vector. So as we saw in the last couple of slides, a unit vector is a vector in a given direction, but with a magnitude of 1. So for example, say we had, again, a vector u. What if we wanted to find the unit vector of u? Well, what we'd be looking for then is a vector in the same direction as u, but with a magnitude of 1. So say this vector u here had a magnitude of 3, for example. A unit vector would then look something like this, right? Same direction, but magnitude of 1. How do we obtain the unit vector then? So we want to keep the direction, but we want to reduce or increase its magnitude to 1. What we do in that case is we have to divide our vector by its magnitude. When we divide a vector by a scalar, remember its direction doesn't change. So we're maintaining the direction, and by dividing by its magnitude, we obtain the unit vector in the same direction with a magnitude of 1. So that was it for this video. I really hope you enjoyed it. I'll be back with more, but in the meantime, check out our website or our YouTube channel to find videos on lots of other subjects such as ESS, chemistry, geography, economics, with even more to come. I hope to see you next time, but most of all, I hope you found this video useful.